So in this lesson, we are continuing on from the past paper questions that we were covering last time. Okay, so we looked at Winter 09, paper 21, question 2, and we looked at enzymes and pH. Okay, so they gave us a whole lot of data. We described how to test for starch. We went through looking at the effect of pH on the rate of hydrolysis. And then we worked on a describe and explaining in bad handwriting and with lots of detail. So today we're moving on to Winter 9, paper 22. We have a look at the question here, and then we have another question from another more recent paper. The thing is with the old papers is that there have been sub-syllabus changes, but if you're careful about which questions you select, then you can have a very valuable resource even with these old papers. Okay, it is still the same thing. Enzymes are still enzymes. Right, so working through that initial breakdown of what is the question actually asking me, what details have I got, we are reminded that sucrase is the enzyme that catalyzes the hydrolysis of sucrose. So here we have our enzyme, and here we have our substrate. Okay, we're told that a student investigated the effect of substrate concentration on the activity of this enzyme. So we're looking at the effect of substrate concentration. So in the back of our minds, we've got that classical curve of initial rate of reaction against substrate concentration. 6 test tubes were set up, each with 10 centimeters cubed of different concentrations of sucrose solutions. So we have varied substrate concentration, which means that this is our independent variable. It's the one that's being set. Test tubes were left in a water bath at 30 degrees C for 10 minutes. After that 10 minutes, 5 centimeters cubed of sucrase solution, here's our enzyme, at 30 degrees C was added to each test tube and the reaction mixtures were stirred. So we have an important thing here. We are controlling temperature. We know that temperature affects the rate of an enzyme reaction, so we have to make sure that it's standard throughout of these so that we can look at the impact of substrate concentration. We don't want to get confused between the two different factors. So whenever you're testing one factor, every other factor that affects a reaction must be kept constant. Right, so we stirred without much details of how we stirred, but perhaps with a glass rod. It's commonly done. Okay, right, so we now have reactions happening. After 5 minutes, the temperature of the water bath was raised to above 85 degrees C. This is very high. Okay, so we need to think about, in the back of our head, what does a high temperature do to this reaction? And the same volume of Benedict's solution was added to each test tube in turn. Right, there's another clue. Benedict's temperature. Right, added to each test tube in turn, the student recorded the time when a green color first became visible in each test tube. So here's your time to first color change. This is now your dependent variable. Okay, it's the one you're measuring. It depends on the substrate concentration. Right, so the concentrations used and the student's results are shown in table 2.1. There's our concentration of sucrose, grams per dm cubed, and it's our independent, sitting nice and happily on the left. Independent, and this is our substrate concentration. And time taken for green color to appear in seconds. Okay, we don't want minutes and seconds, we want seconds only. Nice, neat data. Okay, so this here is indicating how much glucose there is. Whoa, whoops, sorry. I think I just learned how to page down. Glucose is present. Okay, so our enzyme is catalyzing sucrose. Okay, breakdown, hydrolysis of sucrose. So we're creating glucose. So we would have more glucose from more enzyme activity. Okay, we also have to remember that more glucose will give a faster time to change color. So these obviously are not the technical versions of these sentences, and it's quite important to bear that in mind when you go to answer your question. But what you're doing at this phase of getting to know the question is being sure of what it is you're looking at. So now we're happy with what we're looking at. When we have a low concentration of sucrose, we take a long time to get some green color, which means we don't have all that much glucose. On the other extreme, when we have high concentration of sucrose, we have relatively quick time to get that green. We've got lots of glucose around. Right, so first question says, explain why the temperature of the water bath was raised to above 85 degrees C. And here you've got an important thing to consider. You've got 2 marks here for this question, which is an indication that you're going to need 2 valid points. Explain why, 2 points. We've got 2 reasons here. Remember, we raised it to 85 degrees C after 5 minutes. Okay, so after the initial reaction, okay, where it's going to be different. Because remember, when we've got different substrate concentrations, it's just that first bit that's going to be different. So we want to measure that initial rate of reaction. Now we're measuring just the first 5 minutes. Okay, so what's going to happen when we raise that temperature very high? Okay, the high temperature denatures the sucrase, and stops all the reactions simultaneously. Because we can't just take the enzyme out. That's not going to be possible. We need a way to stop them all at the same time. So if we raise all the temperature together, because remember we've got 1 water bath, so let's say we've got a beaker, and we've got all of these test tubes with everything in it. Okay, so it's sitting at 30 degrees C, but let's say it's sitting on a tripod stand with a Bunsen burner underneath, and this is a beautiful diagram. I'm sure you're following exactly what I'm meaning. But you're going to turn that Bunsen on, and your temperature is going to go up. Okay, so take it up to above 85 degrees C, then we know reaction has finished. And because we've done it to them all together, then we're stopping them simultaneously. The other thing is, of course, that we are using Benedict's. And Benedict's needs those boiling water bath in order to get your color change efficiently. So, Benedict's solution, let's say rather testing for reducing sugars. And let's be clear, they know exactly what we're talking about. Products of hydrolysis require testing for reducing sugars, products of hydrolysis with Benedict's solution requires a boiling water bath. So we've been very thorough, we've been very clear, very explicit in our explanation. Because explanations, we must be factual and very clear. Okay, so we are sure now of this 85 degrees C. We now carry on. What is the next question? And funnily enough, seeing as they're from the same session, we have a graph to sketch to show the effect of substrate concentration on the rate of hydrolysis of sucrose by sucrase. So we need to think about a little bit, because we've been given time taken for green color to appear. So how do we get that to a rate of hydrolysis? It's quite nice and simple. We just go 1 divided by the time taken. Okay, because what we're going to do, normally we would have sort of kilometers per hour. We'd have a number on top. Okay, so what we're doing is just presence, absence of green. So presence of green, we indicate it by a 1. So the rate is then 1 divided by time. Okay, so color divided by time. We can't do a color mathematically other than saying presence, absence, 0, 1. So 1 divided by 2, 7, 8. So if we look at our rates, I haven't given myself much space, so we'll put it here in the middle. We've got 0.0036. I did calculate these earlier and write them down. So 1 divided by 145, 0.0069. Same thing again, 0.0105, 0.0133, 0.0213, and 0.0222. Then a reminder again that your classic graph for this situation goes like this. And if we look at these numbers, 0.003, 0.006, we're doubling. 0.01, nearly doubling again. 0.013, not so much of an increase. 0.02, a little bit of an increase, but then 0.2 again. So you can see we've actually got this classic shape. So this is another reminder, yes, we draw these classic graphs with one smooth line, but there's a whole lot of data behind them, individual points, and this is an example of one. Okay, so back down here, okay, we are sketching. We don't have units on this vertical axis, or labels, sorry. So we're not being sort of plotting graphs, but we've got to get an idea of where do we level out, okay? And we leveled out at a concentration of about 50, from 50 to 100, we're constant, we know that. So we look for that 50 point, and we know 50 to 100 is going to be constant, and from 50, we're going down to 0. And that's it. So avoiding all the tails and things that I've got here in the middle. Pencil and paper is slightly easier. Nice smooth curve up to 50 and then flat. Our classic concentration of substrate graph. Then comes your classical question to follow a graph with reference to the student's results. So in other words, quote data, describe and explain. There they are, the pair that works so well together. Give me a description of something, explain why it happens. The effect of increasing substrate concentration on the rate of hydrolysis of sucrose by sucrase. Okay, and we are now halfway through the lesson, and we still have another whole question to work through. So I'm going to do this one in more bullet point form. Okay, so what are the important features that we would be looking at here when we structure an answer? Okay, so describe and explain. Well, our graph has 2 zones roughly. This increasing zone and the flat zone. So let's do a description and an explanation, a description and an explanation. There's 4 valid points. Mark allocation is 5, so we just need to add 1 more explanation point, and then we've got 5 marks. But of course, when you're doing these for revision, when you're doing these for learning, when you're doing these for understanding, you aim to max out. You don't want to just get 5 marks. You want to get maximum marks. So, first description that we see is an increase in rate of reaction up to, let's say, 50 grams per dm cubed. That's where we leveled off. Okay, so in this zone, we want to make reference to the fact of what's limiting the reactive reaction. Okay, and we know, especially when we look down here, we can't have a reaction when we don't have substrate. So substrate concentration is your limiting factor. And because your substrate concentration is limiting, not all your enzymes are busy, so you have available active sites. So remember again, you don't want to talk about available enzymes. Who cares about the rest of the enzyme? The important bit is the active site. So you want to refer to the active site. So there we've got a description with 2 nice explanation points. So now we do the same thing again. So even when you're studying, it can be helpful to use the bullet points because again, it helps you get that structure, that flow, that preciseness and conciseness that is so important for AS biology. So our next description is our constant rate of hydrolysis. So we have a constant rate of hydrolysis from 50 to 100, oh, not 110, 100 grams per dm cubed. Okay, so first point in this question is that Vmax is reached. Maximum velocity, and we're quite happy to use this Vmax terminology. Okay, what happens when we reach Vmax? Okay, a little bit more explanation. Our enzyme concentration is now the limiting factor. Instead of having available active sites, we would have all active sites occupied. And another way of saying this is that to say that the substrate is in excess. If we wanted to increase reaction rate, we would have to increase enzyme concentration at this point. So there you've got sort of a skeletal view of the answer to the question, where you can clearly see the description and then the explanation points linked to that description. So if you're a person who struggles with describe and explain questions, this might be a nice way to look at them and to start working on them in terms of practice. Describe it, explain it, describe the next piece, explain it, and keep yourself on target with what you're doing. Right, so that is the end of that question. Are there any questions in particular relating to this one, or shall we move on to the next pathway question? Okay, so let's move on to a question. This one is from summer 2013, paper 23. Okay, so enzymes again. Okay, so we did have one question come through from the previous one asking about, can you answer the question like this in an exam? Similar to this, yes. So you can answer in bullet points. I wouldn't answer in 2 levels of bullet points like this. And I would make them a little bit more wordy. Okay, so we could say Vmax, put a sort of bullet point on the side and say Vmax has been reached and the substrate is now in excess. Enzyme concentration is the limiting factor as all active sites are occupied. Okay, so hopefully you see the difference between the two. So almost this would be your little notes to self on the side to structure your answer, and then you turn that into full-on bullet points. So again, if you are a person who likes to write sentences that are 6 lines long, consider bullet points. Also consider training in bullet points and then writing short sentences. Okay, they do accept bullet points, they accept sentences, but if you make an error in a sentence, then that whole sentence is marked wrong. So keep them short and sweet, whichever you choose. Okay, so back to our next question. We have an enzyme, catechol oxidase, causing brown color to develop when slices of fruits such as apples are exposed to air. The enzyme catalyzes the following reaction. Catechol plus oxygen goes to catechol oxidase is your enzyme, goes to quinone plus water. Quinone is immediately further oxidized in air to brown. So this one here is oxidized to brown. Both catechol and quinone are colorless. So these two are both colorless. A student investigated the rate of this reaction under different conditions. How could they follow the progress of this reaction? The product of quinone is colorless. Water is appearing, but not so easy to measure the appearance of water on a small scale. Okay, but we have this immediately further oxidized to brown. So we can look for the first appearance of color. Same like with our Benedict's test only here, we're looking for brown. So look for the first appearance of the brown color. But the thing is, you know, this is like an ultimate. So one of the struggles with that Benedict's test and time to first color change is when is it changed? What is green? So let's tell them. We would use a standardized color chart. Let's make it easy. So you could have your piece of apple, and then you could have a color chart with all the different brown colors. And you can say, okay, so this one is the one that it needs to be. And then you look and it's matching and it's straightforward and it's easy and you can see this is the color. Okay, so when you're answering questions in your theory papers or when you're answering modifications to your pracs, you can take this to where would you like to be, not necessarily what you can do. Okay, what would be the best way to do this in your ideal lab setting? Right, so in the first investigation, the student measured the initial rate of the reaction in varying concentrations of catechol. Varying concentrations of catechol. Catechol, remember, here is catechol. This is, again, substrate concentration. And look at this, it's our same classic graph. Initial rate of reaction against concentration of catechol, and up we go. Okay, so explain the results shown in figure 4.1. Note there, only explain, which means that you have no marks for description. If you write a lovely little paragraph about description, nobody actually cares. Okay, unfortunately, no matter how well you can describe it, they are not going to give you marks for it. So, just explaining, and look, we've got that same pattern. We've got nothing, we've got increasing, we've got slowing, we've got flat. So, we can do the same thing again. Okay, so let's do it with a little bit more expansion on the explanation, seeing as we've got 5 marks just for explanation. So let's do it bullet point style, slightly more expanded. Okay, so up to 5 millimeters, not millimeters, micromoles, I'm sorry. So 5 is here. This is where we really now flattened out. Okay. your substrate concentration is limiting, what are we looking at? The initial rate of reaction. Okay, so expand on this. There are free active sites and relatively few enzyme substrate collisions. So not even complexes being formed. They're not even colliding to each other because there's not so many substrate molecules around. Okay? So, again, explanation. As substrate concentration increases, what is the reason why for that increased rate of reaction? We have more enzyme substrate complexes formed. And this increases the rate of reaction, but we're not talking about that description, we're just talking about the explanation. So next explanation is, of course, where we flatten out. So above 5 micromoles, we've got about 5 micromoles of catechol. Enzyme concentration is limiting the initial rate of reaction. Okay, we can say that all active sites are occupied, so increasing substrate concentration further has no effect. Okay, so there you see some slightly more expanded bullet points. And you can see that actually we've got to the point now where we are writing sentences. So it's an easy progression from here to just starting the sentence on the line that the previous one ended, and then you've got a paragraph. So the idea is that you step through, particularly if you're not so good at writing short and sweet sentences. So start out with these, like we did back here, like seriously shortened, sort of what's my main fact. Then you're going to build them into sentence per bullet point, and then you build that into paragraph. And you've got the gradual progression, and what you end up is with short, sweet sentences in a very concise and factual paragraph. We have now a second investigation, repeating the experiment, adding an inhibitor. So sketch on figure 4.1, the results that will be obtained for the second investigation, which is with a competitive inhibitor. So when we have a competitive inhibitor, we have eventually the same thing, because eventually you have high enough substrate concentrations that everything calms down. So we would also get to Vmax, we would just get there much slower. So there is our line with our inhibitor. Explain the effect that PHBA, our inhibitor, will have on the action of phenol oxidase. Okay, so explain, we need these facts. So when we are a competitive inhibitor, main thing is that we are similar to the substrate, we're complementary to the active site. So PHBA is similar in shape to the substrate and is complementary to the active site. Okay, let's actually not do this one bullet points. Let's make sentences now as we're progressing. So, PHBA will bind to the active site, preventing enzyme substrate complex formation. What does this then cause? This reduces the rate of reaction. Okay, so next question says lemon juice contains citric acid. Adding even a small amount of diluted lemon juice to apple slices slows the appearance of brown color. Suggest an explanation for this observation. Remember here, we've got acid. When we've got acid, we're changing the pH. When we change the pH, we change all those bonds in the enzyme. So, enzymes work in a limited pH range. Adding lemon juice changes the pH, making it more acidic. Hydrogen ions interfere with our charge-base bonds, so hydrogen and ionic bonds in the enzyme, changing the shape of the active site. And there we go. So now we've linked everything and we had a nice revision of theory of enzymes as well as doing a past paper question. So when you're ready for that stage of life when you're working through past paper questions, this is the sort of thing that you'll be doing.